Welcome everybody. My name is Jean-Marie Verdun. I'm a senior strategist at HPE, so mostly focused on open platform. I'll be with Jeff Krantz, who should be online right now, who is our senior director of engineering at HPE. And my talk is going to be about open source firmware on top of HPE ProLiant platforms. So a little bit of background about the ProLiant family. The ProLiant family exists since the past 25 years. We introduced the Gen 10 about 12 to 18 months ago. So this is the HPE volume server platforms. That's our top-selling machines deployed worldwide to corporate customers up to SMBs. And the Gen 10 family has been focused on security behavior. So we introduced the Silicon Root of Trust technology, which allow our customers to be sure that the firmware that they're running is the one that they're expecting to run. And this is enabling higher security level and protecting customer assets. Based on this Silicon Root of Trust, we introduced a couple of new technology which are taking care about the global lifecycle of the platform. So the first one is the server system restore, just in case of emergency restore procedures. You can now, as a end users, through a one-click or IDO REST API call, restore the system to a known state. Just as a quick background, IDO is the name of the BMC on top of the ProLiant platform. So this is a custom ASIC developed by HPE, and you can compare it to regular BMC on many platforms, except that IDO has some advanced features which are dedicated to HPE. We also introduced the one-button secure erase, so which is pretty useful when you have to decommission some servers. Through that features, end users can launch a secure erase operation on the drives, removing all the data. So it does require some support from the drive. So there is a new erase features which came up to SATA and SAS drives. So you have to use this kind of devices if you want to use this kind of features. There is also the server configuration lock. So that features enable the detection of hardware modification within a system configuration, and is behaving based on end user requirements, either sending a warning or stopping the bootstrap if there is any modification which has been detected. So the key thing is that since the latest generation of ProLiant, security has become something extremely important at HPE. So we developed a couple of technology based on Silicon Root of Trust, and this technology and security behavior has some direct impact on the firmware, and we will be discussing about it later on during this talk. So why open source firmware? So there are two kind of security model currently, and the first one is through secrecy, and as you might be imagining, this is what we have done within the Gen 10 platform. So everything is proprietary. It relies on well-known technology, but we can reach through that process a very high level of security, and this has been deployed at scale. Unfortunately, when there is secrecy, there is no standardization. And what we see with open source firmware is an opportunity for higher standardization within the firmware industry. This is also easing the deployment at scale between cross-platforms. So meaning that current implementation of HPE firmware runs only on HPE hardware. But we know that the world is not only HPE, this is also our competitors. And most of our customers are running different platforms. And we care about cross-platform deployment and easing the scale-up and the provisioning of the systems. And we see there an opportunity with open source firmware platform. So what we see also is that security by obscurity is not really something which is acceptable everywhere around the world. So some of our customers really care about having HPE taking care about their security. Some of them are really willing to better understand what we are doing. So, and what we see is that the spread is really wide, and we are expecting that we will be needing to offer both options: security through secrecy or obscurity, and security through being fully transparent. And open source firmware is the best answer to the second category. So there is also some major benefits. So we can rely on open source development method to enhance firmware behavior. And what we see with open source firmware is that they are all based on Linux. And as they are based on Linux, it's super easy, or it's far much more easier to find developers and or adapt your process to provision the servers, because everybody knows Linux currently. Not that many people knows how the UEFI shells works, or even the IDO API, because they are proprietary things. And we believe that relying on established technology and well-known technology will be easing the development and the market adoption. Last but not least, a firmware is made to initialize hardware. And what we see is that a single device driver tree is something super important, because we have to take care about qualifying only a single source tree for each device drivers. As an example, so when a firmware bootstrap, it needs to initialize most of the PCI Express devices. And with UEFI, this is done with proprietary firmware, which are provided by device vendors. So these firmwares are using form factors, or are enabling the hardware with their own way of doing it. And then the operating system is redoing the same things. So we believe that if we could rely on the operating system's device drivers at the firmware level, so we can reduce the number of bugs, and this could be something very efficient and well understood by the market. So where do we stand? So right now, the ProLiant has not been designed to support open source firmware, so we must accept it, and this is what happened. But we believe that there is at least a need which has been expressed by many customers to support open source firmware, and we started R&D activity about 12 to 18 months ago to validate that we can run OpenBMC on top of the ProLiant platforms. So we pick up one of our ProLiant servers, so the DL360, which is a 1U pizza box-like servers with HPE enablement, 1010 machines, so based on Skylake processors, and we use it as a development platform. So we try to port OpenBMC and Linuxboot on these machines, and I'm going to discuss about where do we stand regarding that. So the first step has been to rework the Silicon Root of Trust. So as to be a development platform, we need to be able to upload and validate firmware build. And Silicon Root of Trust is designed to lock systems and being sure that the firmware which is run is the one which is expected. And so we manufactured a couple of servers, dozens roughly, as being a development platform, and starting to spread them to open source community and to our firmware engineering, just to use them as a basic development platform. Roughly, this machine has Silicon Root of Trust, which is not fully disabled, but which is configured in a way that we can run properly OpenBMC on top of them. So then we pick up the source code stream from GitHub. So there are many end users who have forked OpenBMC, and we believe what is important is that everybody use the same source tree and try to upstream as much as possible on their source code. And that's why we rely on the GitHub source tree, and we recompiled it as it. We patched it a little, so for as to properly support the IDO ASIC, which is based on an ARM core, and we had to properly adapt the I/O, so roughly GPIO to properly support ProLiant sensor, I2C bus or SM bus, and properly set up the platform. The great news is that we now have an OpenBMC concept which works. So we demonstrated during the latest OCP summit in Amsterdam. So this was, I think, the first time we got this machine out in the wild. And the port is quite stable. So we do encounter a couple of bugs with kernel crash, which are related to hardware implementation of our system BIOS. Flash connectivity to the platform, but we are currently working on fixing that, and we are pretty optimistic on the fact that OpenBMC may be super stable on the ProLiant platform. So right now this is a proof of concept. That's a pure engineering exercise, but we are thinking at moving forward with that proof of concept, and I will show you later on what is required to move forward. So what about system BIOS? So Linuxboot. So we started the development of Linuxboot on the DL360 Gen 10 platforms with SRT disabled, same machine than OpenBMC, exactly the same hardware configuration. And the first step has been to use Linux kernel as a UEFI shell replacement. So we apply roughly what the Linuxboot community did recommend since a couple of months or 1 or 2 years ago. So we pick up the Linux kernel, we replace the UEFI shell and try to boot Linuxboot through that method. Everything works perfectly, but we cannot take all the benefit from Linuxboot approach, because we still have to rely on the whole UEFI stack, which is bootstrapping the servers and load the device drivers tree and then perform the boot of the UEFI shell as being an operating system boot, roughly. So the good news is that we successfully made it. We are able to network boot from that shell and from the Linuxboot environment, but we still have a lot of work. So the next step might be related to shrinking down the number of Dixie drivers which sits inside HPE firmware. So you won't be surprised to know that we are loading a crazy amount of drivers. So we are supporting about 500 UEFI drivers within the ProLiant firmware. This is related to the many device drivers that we have to support on the general purpose servers. And Linuxboot is envisioning a way of starting a machine with a very strict reduced set of device drivers. So we started the process to identify which of these drivers were required to properly bootstrap the servers and shrinking them down. So we successfully removed about 200 of them, and we are still working on getting rid of the hundreds of them which are still there. This does requires a lot of work on the UEFI side from HPE. The great news is that we own our own UEFI BIOS implementation, and all the engineering team is working for HPE. So meaning that we can do it, but the process is going to require a lot of time because we need to refactor our system BIOS solution. We believe that we can do it, and we are currently reviewing the interest to make it happen or not. What we have also identified is that there was some very strong tie between our UEFI implementation and the ILO firmware. So we also need to break that tie, because we are envisioning the fact that we might have customers willing to run OpenBMC and Linuxboot, or Linuxboot and ILO. And what we discovered is that if we do not break the dependency between ILO and UEFI, so we might be facing some implementation issue with open source firmware. So this is ongoing work. The great news is that we have successfully started OpenBMC. We are having proof of concept of Linuxboot. Our OpenBMC proof of concept is more mature than the Linuxboot one, but we also do believe that OpenBMC is also a more mature open source firmware solution than Linuxboot currently. So we are also starting to discuss with our customers about their own requirements. So HPE customers base is a little bit different than OCP pure customer based. So we do address, as I said at the beginning of that talk, a very wide customer base from SMB to corporate end users or cloud service providers. So all of them have different requirements. So we do see some requests at system BIOS level to properly support video, which is not the case currently with Linuxboot. So this does requires that we turn on PCI Express RAM load at the Linuxboot environment. This is doable, but it still requires some work. We clearly have a requirement to support multi-OS. So right now, Linuxboot is mostly focused on Linux. There has been a proof of concept with Windows and VMware, but we need to validate that all of these software environment properly work with a Linuxboot environment before we can scale it. Just to get back quickly on the video support, we also observed that there was no hardware acceleration for the video encoding within OpenBMC. That is acceptable for many customers, but for some of our customers, this might be decreasing the user experience against our regular ILO firmware. So. Last but not least, we think that there is a need for validation, certification, and reinsuring the market that everything is properly under industrial control. So most of the feedback we get from early adopter is that OpenBMC and Linuxboot have not been deployed at scale. So getting reference, publishing that they are using this firmware at scale is getting super important, at least for market acceptance. So we also need a stable version of URoot, so with release cycles and being sure that everything is set up properly. And there are a couple of questions regarding supporting industry standard protocol. So OpenBMC is working on Redfish integrations, but there are a couple of protocol which needs to be supported either at Linuxboot level. It doesn't mean that these requirements are mandatory, but we're just trying to guide the open source firmware community on what might be important in the near term to make this firmware successful at wide scale. So, as I say, testing is going to become critical. And there has been a couple of ongoing efforts to set up continuous integration and testing platforms. So Facebook has introduced during FOSDEM the way they are testing their open source firmware. And I think this is a very important effort, and we are going to try to collaborate and better understand what they have done up to now. On our side, what we think is getting critical is to get more ProLiant machine accessible to the open source community, and with the relevant software development stack, which can enable them to properly test and validate that OpenBMC and Linuxboot works on the ProLiant machine. So this machine will be configured with direct hardware testing capability. So what do I mean by saying that? Roughly, we think that a firmware can be validated only if it's running on real hardware. And making it work on real hardware is a tough work, because when the firmware doesn't work properly, you can break the machine. So most of the time, firmware engineers have access to the hardware. So the hardware is sitting on their desk. They are developing new firmware version. They flash the chip and they put the new chip with the new firmware image directly on top of their motherboard. So providing remote access to hardware requires that this manual process become automatized, and this is on what we focused lately. What we believe also is that we need more than one machine. So we will be trying to scale out our CI platforms and provide a cluster. And this cluster could be potentially directly connected to the GitHub repo of OpenBMC and Linuxboot, and kicking a compile operation each time a new pull request is coming up, and a direct test. So we are also envisioning the fact that from the cluster, we might be providing test firmware for some customers with signatures. We are not sure yet that we are going to make it happen. So we still need to figure out how to do it properly and without compromising the security of the ProLiant platform. This is ongoing works. We are open to discuss with the community on how to do it properly and the most efficient way. So the CI in real life. So what does it mean? So what you can see on this slide is a screenshot of a proof of concept of the CI, which is sitting on the web servers. So roughly, you get access to that CI through a web browsers. You type in the IP address of the CI, and you get access to this screenshot. So on the top level, on the left-hand side, you can load your own build firmware for the ILO chip. And let's imagine this is an OpenBMC. So you drag and drop your firmware image to your browsers. This is uploading the firmware image to the servers. And this is starting what we call a flash emulator. So the firmware is loaded within a flash emulator, which is directly connected to the SPI bus of a ProLiant machine. So the flash emulator is started, and you can decide when to turn on the power on the test machine through the yellow button on the same web page. When you turn on the power, this is going to feed the test ProLiant with the flash emulator connected to, and the ProLiant is going to bootstrap. So on the right hand side, on the gray rectangle on the right hand side, bottom side, you can see the ILO console coming up, and from there, the end users within his own browsers can directly connect to that session. So you can connect to it, you can be root, you can run any kind of command, and you can debug. So if there is a kernel crash, so this is running a screen session. So you can go backward and you can have a look to why the kernel crashed. And that's we believe this is a super efficient way to validate that the run works. If the system crash, you can disconnect the power and reload a new image and reconnect the power. So that's a good way to unbrick a servers. You do not need to reflash any chip. Everything is automatized by using the flash emulator. Let's imagine and envision that your build works. So then you can get access to the embedded web servers from the ILO. And that's also a super efficient way to validate that all the features from OpenBMC works, and you can get access to the host serial port, meaning that if you are also a Linuxboot developers, you can kick Linuxboot on using the same process by loading your image to the BMC and running the servers. And that image is also available through flash emulators. So meaning that you are fully independent from the BMC capability to properly write to the SPI flash. You do not need to rewrite it locally. So that's another way to avoid not breaking. Regarding the reference, so we believe that it is core and super important to use OpenBMC and Linuxboot GitHub repository and upstream everything. This is currently our intent. We didn't upstream anything as of now, but this is clearly our intent. We are currently reviewing the CLA from OpenBMC, and we're expecting to sign it up within the next couple of weeks. So Linuxboot doesn't have any CLA, so it will be far much more easier for us to submit code to the Linuxboot project. And we are strong supporter of the Open System Firmware initiatives, which is running within the OpenBMC community. So I think this is the right time for the Q&A session, and let's start it and discuss about our talk. Thank you very much for for your attendance, and let's go.